Throughout human history, we have built an extraordinary body of knowledge about the universe around us. Yet, despite everything we have learned, we are still only at the beginning of the journey. The cosmos remains a vast twilight zone of secrets, unexplained mysteries, and black holes shaped by forces we cannot directly see. In this video, we will explore some of the most fascinating questions still facing modern science. What lies beyond the universe itself? Does the mysterious Planet 9 truly exist somewhere in the dark outskirts of the solar system? Could life be hiding beneath the frozen surface of Jupiter's moon? And what exactly did Voyager 1 and Voyager 2 discover when they traveled beyond the known boundaries of our solar system? It is often said that the universe has no limits, no beginning and no end. But perhaps by the time we reach the end of this exploration, you may no longer think of the universe as something truly infinite. After all, anything that has a beginning must eventually face an ending. If the universe were truly infinite in both space and time, then it would contain an endless number of stars. In such a universe, the night sky would be flooded with light, so bright that darkness would never truly exist. Yet when we look up, we see a sky filled with darkness between the stars. This simple observation suggests something profound. The universe has not existed forever. According to modern cosmology, the universe began with an extraordinary event known as the Big Bang. Imagine taking a sheet of paper and placing a small dot in the center. Now imagine compressing the entire sheet until everything collapses into that single point. Before the Big Bang, the entire universe may have existed in a state even smaller than that tiny dot. All matter, all energy, everything that would ever exist was compressed into an unimaginably dense singularity. The pressure and temperature inside this state were beyond anything we can truly comprehend. Eventually, that extreme state could not remain stable. Expansion began. Just as a crumpled sheet of paper naturally tries to unfold and return to its original form, the universe itself began expanding outward. But this expansion occurred on a scale so enormous that it created everything we know. Every star, every galaxy, every planet, every atom that makes up our bodies is ultimately a consequence of that moment. In the very first fraction of time, roughly 1/1,000,000th of a second after the beginning, the universe was filled with an extremely hot and dense substance known as plasma. From this seething cosmic plasma emerged the fundamental particles that make up our world today. Protons, neutrons, electrons. Through a process known as nucleosynthesis, these particles combine to form the first simple elements, mainly hydrogen and helium. Over time, gravity gathered these elements together to form the first stars. Inside those stars, the heavier elements were forged. The same elements that would eventually become planets, oceans, and living beings. But before we continue exploring how the universe evolved, we first need to understand how scientists managed to glimpse something remarkable. A faint echo from the very beginning of time itself. And surprisingly, you can see an example of this echo with something as ordinary as an old television. Turn on a television that has no signal and you will see flickering white noise and random interference across the screen. It may look meaningless, but hidden within that static is a tiny reminder of the most ancient event in cosmic history. Look closely, because what you are seeing is connected to the birth of the universe itself. This faint signal is known as relic radiation of the universe, more formally called the cosmic microwave background, often abbreviated as CMB. During the 1970s, as space exploration advanced, scientists began noticing strange regions in astronomical observations that could not be properly explained. Some images appeared to contain something similar to lens flares. Yet the puzzling part was that all known cosmic sources of light at the time, such as dying stars or newly forming stars, were located far away from these mysterious signals. None of them could possibly produce the phenomenon that scientists were observing. That mystery eventually led researchers to the discovery of relic radiation. What appears on a television screen as faint, static, or white noise is actually a tiny glimpse of this ancient radiation. That noise is not random at all. It is the true echo of the early universe. A whisper from the moment when the cosmos first became transparent to light. When scientists began studying this radiation in detail, they realized something remarkable. It originated at the precise moment when the universe first became filled with newly formed chemical elements and light was finally able to travel freely through space. Further investigations showed that this radiation does not come from stars or any modern sources of light. The first detailed map of this ancient glow was created with the help of a space probe called the Wilkinson Microwave Anisotropy Probe, often referred to as WMAP. Later, an even more detailed map was produced by the Planck Space Observatory. If you look at that map carefully, it resembles the static of a television screen. Except now it appears in color. Those colors represent extremely small temperature variations spread across the entire universe. What we are seeing is the fossil light of the Big Bang itself. Radiation that has been traveling through space for billions of years. Because of this light, scientists can now study the large-scale structure of the universe and understand something important. The universe we can observe is not infinite. The region we can see and measure is known as the observable universe. Everything contained within this vast region is sometimes referred to as the meta-galaxy, the portion of the cosmos accessible to observation and scientific measurement. So where are we within this immense structure? If we zoom in step by step, the picture becomes clearer. First, there is our home planet Earth. Earth is part of the solar system. The solar system itself belongs to a small neighborhood of stars known as our local stellar region. That region lies inside a spiral galaxy called the Milky Way. The Milky Way in turn belongs to a much larger structure known as the Laniakea supercluster, a vast collection of thousands of galaxies bound together by gravity. And beyond that lies the observable universe itself. Seen from this perspective, humanity occupies a place that is astonishingly small. Little more than a grain of sand within an immense cosmic ocean. Yet even something as vast as the observable universe may still have limits. This leads to one of the most profound questions in cosmology. Is everything we can see truly the full extent of the universe? To approach that question, scientists examine the cosmic microwave background once again. On its map, the brighter regions indicate small changes in temperature. These fluctuations reveal where matter later gathered to form stars, galaxies, and enormous clusters of galaxies. But there are also regions beyond what our telescopes can directly observe. Could relic radiation help us see the entire universe? Imagine standing under the night sky next to a bright campfire or on a brightly lit street. The nearby light makes it difficult to see faint, distant stars. The same principle applies on a cosmic scale. Relic radiation illuminates the universe and allows us to see its structure. But at the same time, its glow hides some of the darkest regions of space. It can conceal enormous cosmic voids, distant black holes, and parts of the universe whose light has not yet had time to reach us. The consequences of the Big Bang are still shaping the universe even now. This naturally leads to another question. If the observable universe has an edge, what lies beyond it? One possible answer comes from a concept known as inflation theory. According to this theory, in the earliest moments after the Big Bang, the universe expanded at an incredibly rapid and exponential rate. That expansion may still be continuing today. If this idea is correct, then the universe may not have a simple physical boundary at all. Think again about the sheet of paper you crumpled earlier. Over time, it slowly unfolds, gradually returning to its original shape. The universe may behave in a somewhat similar way, expanding outward from its original compressed state. However, even this theory raises new questions. The laws of physics appear to operate in exactly the same way everywhere we observe them. If that is true, why did the universe begin expanding in the first place? Where did the enormous energy required to create the universe come from? Astronomical observations clearly show that galaxies are moving away from one another at ever-increasing speeds. At first glance, this seems to support the idea of cosmic inflation. Yet the deeper scientists look, the more questions appear. What existed before the universe formed? If everything began from a singularity, did anything exist before that singularity? If the laws of physics are universal, why is the universe so vast? These questions have troubled scientists for decades. The Big Bang Theory and the inflation model explain many observations. But they do not answer everything. As knowledge expanded, new ideas began to appear. One of the most intriguing proposals is known as the cyclic universe, sometimes called the oscillating universe model. According to this concept, the universe may behave like a living system, with repeating phases of expansion and contraction. The foundations of this idea were first developed in the early 20th century through what is known as the Friedmann-Robertson-Walker model. This model suggests that if the universe has been expanding since the Big Bang, then at some point in the distant future the expansion might slow down and reverse. The universe would eventually collapse back into a dense singularity before beginning a new cycle of expansion. However, this elegant idea encountered a serious problem. In the 1930s, scientists discovered the concept of entropy, the natural tendency for energy to disperse and systems to move toward disorder. Entropy implies that with each cosmic cycle, the universe would lose usable energy. Every new cycle would require more energy than the previous one, and scientists could not explain where that energy would come from. Because of this contradiction, the cyclic model was largely abandoned for many decades. But at the beginning of the 21st century, the idea returned in a new form. Two scientists from Princeton, Paul Steinhardt and Neil Turok, proposed a revised version of the cyclic universe model. Their theory was inspired by concepts from string theory, which suggests that everything in the universe is built from incredibly tiny vibrating structures, often described as strings. According to this framework, everything in the universe is built from incredibly tiny constituents that behave somewhat like vibrating strings. Matter and energy are not fundamentally different things, but different expressions of these microscopic structures. For example, the smallest particle of light is called a photon, and what we perceive as a beam of light is actually an enormous number of photons moving together in the same direction. The same underlying principle can also describe many other phenomena, including heat, gravity, and even sound. Within this perspective, the universe may not have a true beginning or a final ending. Instead, it could be an endless sequence of transformations involving these fundamental strings of matter and energy. In such a scenario, the history of the cosmos is not a single story that began once and will eventually end. Rather, it is an ongoing cycle of phases in which the universe repeatedly changes its state. One particularly intriguing version of this idea proposes that our universe formed when two three-dimensional worlds collided with one another. At first, this sounds strange because we only perceive the familiar three dimensions of space. Yet according to string theory, the universe may actually contain additional hidden dimensions beyond the ones we experience directly. Matter might exist within these extra dimensions in ways we cannot observe. In some theoretical models, there could be dozens of dimensions, possibly even as many as 50. If such dimensions exist, then it becomes conceivable that two three-dimensional universes could move through a higher dimensional space and eventually collide. When such a collision occurs, the enormous kinetic energy released by the impact would transform into fundamental particles such as quarks, electrons, and photons. That conversion of energy into matter would resemble the conditions we associate with the Big Bang. In this interpretation, the birth of our universe would not be the absolute beginning of existence, but simply the start of a new cosmic phase triggered by the interaction of two larger structures. In this model, the colliding worlds transfer energy to each other. That energy drives the expansion of the universe and eventually allows matter, stars, and perhaps life to form. But this expansion cannot continue forever. Over extremely long periods, the energy responsible for the expansion would gradually dissipate. When that happens, the universe would slowly begin to contract once again. Expansion would be followed by compression, completing another stage of the cosmic cycle. If this picture is correct, then the universe does indeed have an edge. But not in the sense of a physical wall or boundary in space. Instead, the edge marks the end of one cosmic phase and the beginning of another. It is the moment when one cycle concludes and the next one begins. In this sense, the boundary of our universe may lie where it interacts with other universes moving through higher dimensional space. Beyond the familiar three-dimensional world we inhabit, the laws of physics may behave in ways we do not yet understand. For now, the cyclic universe remains a fascinating but unproven idea. The greatest challenge facing scientists today is finding experimental evidence for the existence of extra dimensions. At present, their existence is supported only by theoretical calculations. The simple sheet of paper we imagined earlier provides a helpful analogy. When you crumple that sheet of paper, you are the external force that alters its shape. You control when the compression stops and when the sheet begins to unfold again. In a similar way, humanity is still trying to determine what force triggered the transformation that gave birth to our universe and what forces will shape its future. Whether the catalyst was a collision with another universe, the Big Bang itself, or something even more mysterious remains unknown. Yet step by step we are moving closer to understanding the answer. Closer to looking beyond the edge of the cosmos and finally explaining why everything exists. Since Pluto lost its official status as a planet, scientists have continued searching for other large objects in the distant outskirts of the solar system. Evidence suggests that something beyond the orbit of Neptune is influencing the paths of many small celestial bodies, such as asteroids and dwarf planets. Whatever this object is, it cannot easily be seen through telescopes. Some researchers have even suggested that the mysterious influence might come from something unusual. Perhaps a miniature black hole or a concentration of dark matter. Today we will explore one of the most intriguing possibilities: the existence of a mysterious Planet 9. We will examine what this object might be, how large it could be, and whether it is truly a planet at all. Interest in Planet 9 grew dramatically when astronomers began carefully studying the motions of objects far beyond Neptune. These distant bodies, known as trans-Neptunian objects, orbit the Sun within a region called the Kuiper Belt. This distant zone of icy debris resembles a vast asteroid belt located at the edge of the solar system. Two astrophysicists, Konstantin Batygin and Michael Brown, examined 6 distant objects within the Kuiper Belt, including the dwarf planet Sedna. They discovered something unexpected. All 6 objects followed elongated elliptical orbits that pointed in roughly the same direction, even though they moved at different speeds. Brown compared this phenomenon to a clock with 6 hands rotating at different speeds, but somehow all pointing to the same position when you look at it. Such alignment should be extremely unlikely. Even more puzzling was the fact that the orbits of these 6 objects were tilted at nearly the same angle, about 30 degrees downward relative to the plane in which the 8 known planets orbit the Sun. The probability of this happening purely by chance is estimated to be roughly 0.7%. One early explanation suggested that the combined gravity of objects within the Kuiper Belt might produce this effect. But calculations showed that the belt would need to contain 100 times more mass than it actually does for this explanation to work. Computer simulations also revealed that a small planet would not have enough gravitational influence to produce the observed alignment. However, when scientists ran similar simulations using a much larger planet, roughly comparable in size to Uranus or Neptune, the models suddenly began to reproduce the real observations. This result allowed Batygin and Brown to estimate the possible properties of this hypothetical world. Their calculations suggested that Planet 9 might have a mass between 5 and 20 times greater than the mass of Earth, and a diameter roughly 2 to 4 times larger than our planet. Detecting such a distant world directly would be extremely difficult. It would lie far beyond the region where sunlight is bright enough for ordinary telescopes to easily detect reflected light. Instead, astronomers would have to search for the faint infrared glow emitted by the planet itself. Yet even this method is challenging. A planet with only 5 times the mass of Earth would not emit much heat. Furthermore, such a distant object would orbit the Sun extremely slowly. making its movement difficult to detect unless astronomers compare images of the sky taken many years apart. Current estimates suggest that the orbit of Planet 9 may lie somewhere between roughly 380 and 980 astronomical units from the Sun. 1 astronomical unit is the average distance between Earth and the Sun. At such enormous distances, the region of sky that must be searched is enormous, spanning hundreds of square degrees. For comparison, the full moon occupies only about 0.2 square degrees in the night sky. To refine their predictions, researchers created computer models representing the solar system 4 billion years in the past. These simulations allowed them to examine how the gravity of the known planets and the hypothetical ninth planet could influence thousands of Kuiper Belt objects over time. Although the work of Batygin and Brown demonstrated that something unusual appears to be influencing distant objects in the solar system, more recent studies have begun to challenge the existence of a massive hidden planet. Between the years 2020 and 2022, astronomers discovered nearly 300 additional objects in the Kuiper Belt region. Observations conducted with powerful telescopes in Chile surveyed nearly 87% of the sky visible from the southern hemisphere over a period of 6 years. When scientists analyzed the orbits of these newly discovered objects, they found that nearly all of them could be explained using ordinary gravitational interactions with known planets. Only 2 objects displayed behavior that remained difficult to explain. Out of 300 objects, such anomalies are statistically small and may even support alternative explanations. This raises an important question. Why do the newest observations not match the original predictions for Planet 9? One possibility is that the ninth planet simply does not exist. But another explanation suggests that the unusual orbits may instead be caused by the combined gravitational influence of many smaller objects scattered throughout the distant outer solar system. According to some astronomers, the strange orbital behavior of objects in the farthest reaches of our solar system may not require the existence of a hidden ninth planet at all. Instead, it might be explained by the combined gravitational influence of countless small bodies orbiting beyond Neptune. In this alternative model, researchers propose the presence of a vast disk made of icy debris scattered far past Neptune's orbit. Collectively, this disk could contain a mass several times greater than Earth. And its combined gravitational pull might be enough to shape the unusual orbits observed among distant trans-Neptunian objects. To explore this idea, scientists built computer simulations that included the known planets of the solar system, the gravity of thousands of distant objects, and a massive debris disk beyond Neptune. When the hypothetical Planet 9 was removed from the model and replaced with a wide distribution of smaller objects, the results were surprisingly similar. The collective gravitational attraction between these bodies could reproduce many of the eccentric orbits observed in reality. Earlier estimates suggested that the total mass of objects beyond Neptune was only about 1/10 the mass of Earth. But for this new model to work, the Kuiper Belt and surrounding regions would need to contain between a few and 10 Earth masses of material. If this turns out to be true, the strange orbital architecture of distant objects might simply be the result of many small gravitational influences acting together, rather than a single hidden planet. To test the idea further, another group of scientists analyzed data from the Infrared Astronomical Satellite and the Keck Infrared Telescope. These surveys were conducted more than 20 years apart, allowing astronomers to search for objects that might have moved across the sky over time. The researchers assumed that any distant planet would likely lie close to the equatorial plane of the sky, and began examining potential candidates. More than 500 objects were identified during the search. However, when their spectra were analyzed, most of them turned out not to be planets at all. Instead, they were far more familiar cosmic objects, faint nebulae, clusters of small bodies, or even distant galaxies whose infrared glow made them appear planet-like at first glance. A nebula, for example, is a cloud of interstellar gas that emits infrared radiation, because infrared light corresponds to heat. These clouds can sometimes appear as faint glowing objects in telescope data, easily mistaken for something else. With each candidate ruled out, astronomers were left with an increasingly puzzling question. What kind of object could possess enough mass to alter the orbits of distant celestial bodies and yet remain completely invisible to us? This question led some theorists to propose an even more radical possibility. What if the mysterious object at the edge of our solar system is not a planet at all, but a tiny black hole? Such an object would be extraordinarily difficult to detect directly. Black holes emit no light. But according to theoretical physics, they can produce a faint form of radiation near their event horizons, known as Hawking radiation. However, this idea introduces another contradiction. Black holes normally form when extremely massive stars collapse. The remnants of such stars typically have masses several times greater than our Sun. Yet the object needed to explain the outer solar system's anomalies would have a mass only 5 to 10 times that of Earth. How could such a small black hole exist? One possibility comes from conditions in the very early universe. During the first moments after the Big Bang, regions of space may have been dense enough to collapse directly into primordial black holes, far smaller than those formed by dying stars. Astronomers from Harvard University have even proposed ways to search for such objects. As part of the Legacy Survey of Space and Time conducted by the Vera Rubin Observatory, scientists plan to look for flashes of light produced when a tiny black hole collides with objects in the Kuiper Belt or the distant Oort cloud. The Oort cloud may contain trillions of icy bodies surrounding our solar system. If one of these objects were to fall into a hidden black hole, the collision could produce a brief but detectable burst of radiation. If such an object were discovered, it could transform our understanding not only of the solar system, but also of how black holes formed in the early universe. Yet even this is not the most exotic possibility. Some researchers suggest that the mysterious object influencing the outer solar system could be something far stranger, a planet made primarily of dark matter. Dark matter is invisible, but its presence is inferred through gravity. Stars orbit too quickly around galactic centers, and entire galaxies move through clusters faster than visible matter alone could explain. One hypothesis suggests that dark matter might occasionally clump together into compact objects roughly the size of Neptune. These so-called dark matter planets would be almost impossible to observe directly. However, they might attract ordinary gas, forming an atmosphere of hydrogen and helium around an invisible core. Under certain conditions, the compression of these gases could raise temperatures high enough to trigger nuclear fusion, producing faint radiation that astronomers might eventually detect. If dark matter planets exist, they likely formed very early in the history of the universe, when ordinary matter was still too hot to form large structures. Because dark matter does not interact with light, it could gather into compact objects long before normal planets existed. Such worlds would be unlike anything we know. Imagine descending through a glowing atmosphere of hydrogen, warmed by gravitational compression. Beneath it would lie a dense layer of helium, and beyond that, something even stranger. At the center of the planet there would be nothing visible at all. The core would be composed entirely of dark matter, completely transparent, invisible even as it exerts immense gravitational pull. You would find yourself suspended inside a luminous shell of gas and plasma surrounding an unseen mass. It would be one of the most alien environments imaginable. What is so special about our solar system? Some scientists believe that our Sun was born from the remains of a nearby supernova. When a massive star exploded somewhere in our galactic neighborhood, its shockwave compressed vast clouds of gas and dust. Over time, gravity pulled this material inward until the pressure and temperature at the center became high enough to ignite nuclear fusion. A new star was born. That star became our Sun. But the Sun did not form alone. Not all of the material collapsed into the newborn star. The remaining gas and dust flattened into a vast rotating disk surrounding it. Inside this swirling disk, gravity slowly gathered particles together. Some of these clumps grew large enough to become planets. Others remained smaller, eventually becoming asteroids, comets, and dwarf planets. Somewhere inside this cosmic disk, the future cradle of humankind began to take shape. In its earliest days, Earth looked nothing like the blue world we know today. It was a violent and hostile place, more like a boiling ocean of lava than a solid planet. The surface was molten rock, constantly churning under temperatures exceeding 1200 degrees Celsius. There was no breathable air. The atmosphere consisted mostly of carbon dioxide, nitrogen, and thick clouds of steam. Meanwhile, the young Earth was under relentless attack. Comets and meteorites bombarded the planet continuously. Some were drawn in by Earth's gravity. Others were captured by the sun and sent hurtling through the inner solar system. Inside, many of these icy bodies were tiny amounts of water. But at this stage, Earth was still far too hot for oceans to exist. Then came the most violent event in Earth's history. A young planet roughly the size of Mars, later named Theia, collided with the early Earth. The impact was catastrophic. Enormous fragments of rock were blasted into orbit around the planet. Over time, those fragments gathered together and formed our moon. In the early days, the moon orbited much closer to Earth, only about 20,000 kilometers away. Its presence would later play a crucial role in stabilizing our planet. Gradually, Earth began to cool. As the surface temperature dropped, a solid crust started to form. Beneath this crust, the core remained molten, composed mainly of iron and nickel. The movement of this liquid metal deep inside the planet generated Earth's magnetic field, a shield that protects us from harmful solar radiation even today. Around 3.8 billion years ago, something remarkable happened. The first rains began to fall. At the same time, the solar system was still full of debris left over from its formation. Meteorites continued to strike Earth, many of them containing small quantities of water and ice. Over millions of years, these impacts delivered enormous amounts of water to the planet. The rain did not fall gently as it does today. Earth was spinning much faster back then. A full day lasted only about 6 hours. Storms were unimaginably violent. Yet through this chaos, something extraordinary occurred. The first oceans began to form. Meteor bombardment continued for nearly 20 million years. Each impact added only a tiny amount of water, but together they accumulated into something vast. Quantity eventually became quality. Scientists have long debated the origin of Earth's water. One theory suggests that most of it arrived aboard meteorites and comets. Another proposes that water was already present inside the young planet and was released through volcanic activity. Modern research suggests that both ideas may contain some truth. Studies of lunar soil have shown that the young sun once emitted intense radiation capable of stripping away volatile substances, including water, from nearby planets. This makes it difficult to determine exactly how much of Earth's water formed locally and how much arrived from space. But one thing seems clear. The collision between Earth and Theia likely accelerated the cooling of the planet and helped trigger the formation of the atmosphere. And that atmosphere became the protective shield that made life possible. Even after the surface cooled, volcanic activity remained intense. Volcanoes released enormous amounts of gas and water vapor into the atmosphere. As the planet cooled further, this vapor condensed into clouds. Then came rain. For millions of years, rain fell across the entire planet. Water gathered into lakes, then seas, and eventually vast global oceans. But these oceans were far from calm. Because the moon orbited much closer to Earth at the time, its gravitational pull generated enormous tides. Combined with hurricane-force winds, sometimes approaching the speed of sound, the oceans were constantly raging. Some waves may have reached heights of hundreds of meters. In this violent environment, scientists believe the earliest forms of life may have begun to appear. Most modern theories agree on one thing: the ancient oceans provided ideal conditions for life to emerge. Yet a crucial question remains. How did the basic building blocks of life, organic molecules, first form? The early atmosphere contained mostly nitrogen, hydrogen, carbon dioxide, and water vapor. These are simple, inorganic chemical elements. The Russian scientist Alexander Oparin, in 1924, and later the British biochemist J.B.S. Haldane proposed a remarkable idea. They suggested that lightning in the early atmosphere could trigger chemical reactions between these gases. During the constant storms of early Earth, electrical discharges may have transformed simple inorganic molecules into more complex organic compounds. These organic molecules would then fall into the ocean, gradually accumulating into a rich chemical mixture sometimes called the primordial soup. Inside this chemical soup, molecules slowly began to organize themselves. Some structures behaved in ways that resembled living cells. They could grow, divide, and absorb surrounding chemicals. But molecules alone are not enough to create life. Life requires information, instructions that tell cells how to function. Today, those instructions are stored in DNA, the molecular library that contains the blueprint of every living organism. Another molecule, an A, plays a crucial role in reading and carrying out those instructions. Over hundreds of millions of years, the earliest life forms remained extremely simple. They were single-celled organisms known as prokaryotes. Unlike modern cells, they had no nucleus and no internal compartments. Bacteria are examples of such organisms that still exist today. Then something revolutionary happened. Some ancient microbes evolved the ability to use sunlight as a source of energy, through a process we now call photosynthesis. These organisms began converting water and carbon dioxide into glucose, their first food using energy from sunlight, and, as a byproduct, they released oxygen. At first, oxygen was actually toxic to many early life forms, but gradually it accumulated in the atmosphere, transforming Earth forever. Between 3.5 and 2.5 billion years ago, oxygen levels rose dramatically. Eventually, new types of cells appeared: eukaryotes, organisms with more complex internal structures and protective membranes. These cells became the ancestors of all complex life on Earth. Over time, life spread through the oceans. Structures known as stromatolites, built by colonies of microorganisms, formed vast underwater ecosystems. Later, algae evolved the ability to reproduce sexually, accelerating evolutionary change. Around 540 million years ago, life on Earth experienced an extraordinary burst of diversity known as the Cambrian explosion. Within a relatively short geological period, most of the major groups of animals appeared. Life continued to evolve. Plants spread across land. Insects took to the air. Fish developed limbs capable of supporting their bodies outside water. One remarkable transitional creature was Tiktaalik, a fish with limb-like fins that allowed it to move in shallow water and occasionally crawl onto land. Over millions of years, amphibians evolved into four-legged vertebrates known as tetrapods. From these early pioneers came reptiles, birds, mammals, and eventually primates. But evolution was never smooth. Mass extinctions repeatedly reshaped life on Earth. The Permian extinction, for example, wiped out about 90% of marine species. Yet life endured. After the age of dinosaurs ended with another catastrophic asteroid impact, mammals began to flourish. And from those mammals eventually emerged a species capable of asking a remarkable question. How did all of this begin? Earth appears to possess a rare combination of conditions that allowed life to arise: liquid water, a protective atmosphere, a magnetic field, and a stable orbit around a long-lived star. Yet the origin of life itself remains one of science's greatest mysteries. What we do know is that somewhere in the ancient oceans, in a world of storms and volcanic heat, simple molecules began a journey that would eventually lead to forests, animals, and conscious minds capable of wondering about their own origins. And in that sense, the story of life on Earth is not just a story of biology. It is a story written across billions of years of planetary evolution, a transformation from the inanimate to the living. And we are living in the remarkable moment when humanity is finally beginning to understand that story. Matter is coming closer than ever to being understood. And in a way, we can almost envy ourselves for living at this moment in history. After all, the secret of life may soon be revealed. But is life possible anywhere beyond our home planet? And what if there were a place in our own solar system where an ocean holds twice as much water as all of Earth's oceans combined? That ocean lies hidden beneath an ice shell dozens of miles thick. From beneath that frozen crust, geysers rise as high as 125 miles. And the atmosphere of this world contains oxygen. It sounds familiar, doesn't it? That is why today we are heading somewhere almost in our cosmic backyard. We are heading to Jupiter, to explore the depths of its icy moon. Europa. Europa is one of Jupiter's major moons. It was discovered in 1610 by Galileo Galilei, along with 3 other moons now known as the Galilean satellites. At the time, this discovery caused a sensation. And even today, Europa remains one of the most fascinating targets in planetary science, drawing attention from astrophysicists, geologists, and biochemists alike. Jupiter and its moons are sometimes described as a miniature solar system. And for good reason. Each moon has its own remarkable character. From the volcanic violence of Io to the strange landscapes of Ganymede, there is a great deal to study on every one of them. That is why missions to Jupiter continue to capture scientific interest. One such mission is JUICE, whose goal is to observe and study the icy moons of Jupiter. We already know that on Earth, wherever there is water, life often follows. So, the search for water has become one of the central strategies in the search for life elsewhere. But is water alone enough? We cannot yet define all the conditions required for life across the universe with certainty. What we can do is begin with the only example we know for sure: Earth. On our planet, water is the first essential ingredient for life. As we understand it, it dissolves nutrients, transports chemicals, and helps living systems remove waste. Many signs suggest that liquid water may exist beneath Europa's ice. And one of the strongest clues comes from a comparison with places here on Earth. The double ridges and fractures visible on Europa resemble ice formations found in Greenland. On Earth, structures like these are often linked to pockets of liquid water trapped within or beneath the ice. That similarity led scientists to suspect that Europa's cracks may also point to hidden water below the surface. The chemical ingredients needed for life may also be present there. Images taken by Voyager allowed scientists to study Europa's icy crust and suggested that the surface contains significant amounts of salts and minerals, including magnesium compounds. These may help explain the reddish or brownish tones seen in parts of the ice. On Earth, similar features can appear where salty material is brought upward through ice by geological activity. On Europa, the movements of the ice appear to resemble tectonic behavior, suggesting that internal activity may be reshaping the surface. The last essential ingredient is energy. Sunlight powers life on Earth, but on Europa the sun is far weaker. Jupiter is about 5 times farther from the sun than Earth is. and that means much less solar energy reaches Europa. Still, Europa receives energy in another way. As it moves through Jupiter's intense radiation environment, the Moon's surface ice is bombarded by energetic particles. That process can split molecules and release oxygen, which helps explain why Europa's extremely thin atmosphere is composed mainly of oxygen. On Earth, oxygen plays a major role in organic chemistry and metabolism. If some of that oxygen is transported beneath Europa's ice, it could provide a source of chemical energy for living organisms, even if they are only microbial. It is also possible that life on Europa, if it exists, may not depend on oxygen at all. Anaerobic organisms exist on Earth, and in the early history of our own planet they were once the dominant form of life. Another factor scientists hope to confirm is geological activity deep below the crust around Europa's rocky interior. In Earth's oceans, hydrothermal vents appear where tectonic plates interact, and these regions are surrounded by astonishingly rich ecosystems. Even in total darkness, life flourishes there. Scientists suspect that Europa's constant flexing under Jupiter's gravity may drive similar processes on the seafloor of its hidden ocean. If that is true, then hydrothermal regions beneath the ice could be some of the most promising places in the solar system to search for life. In other words, Europa may possess all the core ingredients needed for biology. Now let us look at why scientists have become so confident in this possibility. After the discovery of Europa and the other large Jovian moons, it took almost 400 years before their true uniqueness began to emerge. In the 1960s, ground-based observations showed that Europa's surface was dominated by water ice. Much like many other solid bodies in the outer solar system, at first glance it seemed like just another frozen moon. But closer study revealed something unusual. Europa's surface was extraordinarily bright. Its ice appeared cleaner and younger than expected. That suggested the surface had been renewed relatively recently. To understand why, scientists needed a closer look. That opportunity finally arrived with the Voyager missions, which photographed Jupiter's moons in far greater detail. The images transformed scientific understanding of Europa. Voyager revealed a world brighter than Earth's moon, crossed by long bands and ridges, yet strangely lacking large impact craters, tall cliffs, and massive mountains. Compared with other icy moons, Europa looked smooth and unexpectedly fresh. That was surprising because every solid object in the solar system is constantly struck by meteorites. On Europa, those scars were faint or missing. Researchers also noticed that some dark fractures had matching edges, almost like puzzle pieces pulled apart. Between them was darker icy material that seemed to have welled up and frozen in place. This suggested that Europa's surface had been moving and reshaping itself, at least in the geologically recent past. If the surface is so young, something must be erasing the traces of older impacts. One possibility is that warmer ice or slushy material rises from below and resurfaces the moon. Another is that the surface ice slowly sinks under its own weight, dragging crater marks down with it. In either case, the conclusion is the same. Europa's icy shell is not static. It is active, dynamic, and likely influenced by a warmer layer underneath. Scientists also found that the fracture patterns on Europa did not match the shapes expected if the ice shell were completely rigid. The simplest explanation was that the surface was moving somewhat independently from the deeper interior, something that would make sense if a layer of liquid water or warmer, softer ice existed below the crust. That idea pushed scientists to investigate Europa even more seriously. Then came the Galileo mission. Galileo was launched in 1989 and entered orbit around Jupiter in 1995. Its mission included repeated flybys of Jupiter's 4 largest moons, The data Galileo returned from Europa was so compelling that the mission was extended, eventually carrying out a total of 12 close flybys of the icy world. One of the most important discoveries came from measurements of Jupiter's magnetic field near Europa. Galileo found a strange magnetic disturbance in the space around the Moon. The most likely explanation was extraordinary. Beneath Europa's frozen crust, there appeared to be a global ocean of salty liquid water. Only a large conducting body like a saltwater ocean could produce such an effect. At that point, scientists became increasingly confident that Europa really does hide an ocean under its surface. But that was only the beginning. Later studies of Earth's Antarctic ice shelf uncovered a strange form of underwater ice growth. And researchers realized that something similar may happen on Europa. In a sense, it may even snow upward there. The reason is simple. Certain forms of ice are less dense than salt water, both in Earth's oceans and, potentially, in Europa's hidden sea. Because Europa's ice shell is so thick, this buoyant ice may form deep below and rise upward toward the crust, creating structures that resemble mountains growing from beneath the surface. Another sign of activity came from geysers erupting through the ice. Over the past 10 years, scientists have reported evidence for these plumes several times. Some may rise to heights of at least 125 miles. According to current estimates, Europa's ocean may be roughly 35 to 65 miles deep, while the overlying ice shell may be around 12 to 20 miles thick. The interaction between the subsurface ocean and the ice above it, combined with tidal flexing as Europa orbits Jupiter, may generate enough heat and stress to crack the ice open. Through those fractures, warmer ice or even water can sometimes erupt upward as plumes. One of these possible geysers may even have been glimpsed by Galileo, although no samples could be collected at the time. At the same time, there is another important detail. As cracks open in Europa's ice, oxygen from the surface may be carried downward beneath the crust. That is yet another reason scientists take the possibility of life there so seriously. And now that we have a clearer picture of Europa in mind, all that remains is to wait. Because alongside the mission we mentioned earlier, another journey has been planned. One devoted almost entirely to this remarkable moon. That mission is Europa Clipper. It was designed to study Europa in extraordinary detail and determine as clearly as possible whether this icy world may offer conditions suitable for life. NASA equipped the spacecraft with 9 scientific instruments for that purpose. These include cameras and spectrometers that will capture high-resolution images of the surface and help determine its composition. In other words, the mission will not simply show us what Europa looks like. It will help us understand what we are actually seeing. Another key instrument is radar, which will probe the ice shell, estimate its thickness, and search for buried lakes, much like the hidden lakes found beneath Antarctica's ice. A magnetometer will measure the strength and direction of Europa's magnetic environment, allowing scientists to estimate the depth and salinity of the hidden ocean. Thermal instruments will search for warm regions and recent eruptions, while other tools will examine tiny particles and traces of water in Europa's thin atmosphere. By combining all of these measurements, scientists hope to build the most complete picture of Europa ever assembled. It may even spare future missions from having to drill blindly through miles of ice just to answer the most basic questions. Once the spacecraft reaches the Jovian system and begins its flybys, the mission is expected to do far more than simply map the Moon. After the Hubble Space Telescope detected a water plume above Europa's South Pole in 2012, scientists began hoping that a future spacecraft might pass through one of these eruptions and directly sample its material. That is one of the great hopes for Europa Clipper. Over the course of roughly 45 to 50 flybys, the spacecraft will search for places beneath the ice where life might be possible. The improved images will also help scientists identify the most promising locations for future exploration. Some flybys may bring the spacecraft as close as 25 miles above the surface. For comparison, Galileo came only to about 160 miles at its closest. Of course, getting even nearer would be ideal. But Jupiter's radiation is so intense that no spacecraft can safely linger there for long. Power is another challenge. Europa is so far from the Sun that solar panels operate much less efficiently than they do near Earth. Even so, the planned observations should be enough to transform our understanding of the Moon. Scientists are already thinking beyond Clipper. After this mission, and after its data are fully analyzed, future plans may include landing a robotic probe on Europa itself, one capable of penetrating deeper into the ice. And perhaps, if we are fortunate, that is when humanity may finally discover extraterrestrial life. For now, all we can do is wait and look forward to what comes next. Not long ago, one of the strangest stories about the Voyager probes began circulating in an online discussion thread. According to the post, an unnamed NASA employee claimed that Voyager 1 had not merely stopped transmitting its location properly, as had been publicly described. The user also claimed that the spacecraft had recorded a strange low humming sound, and that buried inside it was a message in Morse code. Supposedly, when the message was decoded, it resembled the sounds from the golden record playing on repeat, as though something had found the probe and was trying to answer back. NASA never commented on the story. The tale is almost certainly fictional, but it captures something real about Voyager. Its story has always felt slightly unreal, filled with astonishing discoveries, eerie mysteries, and the unsettling sense that it has traveled to a place where certainty begins to fade. Most importantly, where did all of this happen? It happened at the threshold where established knowledge gives way to theory, beyond the heliopause. But to understand why that matters, we need to go back to the beginning. How did humanity come to explore one of the greatest mysteries in space? And what did we think we knew before Voyager changed the picture? In 1977, Voyager 2 and Voyager 1 left Earth and began their long journey toward the giant planets of the outer solar system. At first, the mission was expected to last only 4 years, but it far outlived that modest plan, and the spacecraft eventually pushed into regions that no one had realistically hoped to reach. Originally, the Voyagers were built to study and photograph the distant worlds of Jupiter, Saturn, Uranus, and Neptune. Their launch timing was no accident. It took advantage of a rare alignment in which the outer planets were positioned in such a way that a spacecraft could visit them in sequence. This opportunity comes only about once every 176 years. Scientists understood how extraordinary that window was, and they did everything possible not to miss it. The idea was elegant. Each planet would use its gravity to bend the spacecraft's path and increase its speed, effectively handing it off to the next planet like runners passing a baton. This gravitational assist made the mission possible. In doing so, the Voyagers set records of their own. Voyager 1 became the fastest human-made object ever sent outward from Earth and remains the most distant human-made object ever created. Voyager 2 earned its own distinction as the first and only spacecraft to visit all 4 giant planets of the solar system. But the mission had another goal as well. Beyond the planets lay something even more profound: interstellar space. Put simply, interstellar space is the region where the sun's direct influence fades away, where its wind, heat, and magnetic dominance no longer define the environment. The region over which the sun's influence extends is called the heliosphere. In the broadest practical sense, that is the bubble that surrounds our solar system. The great question was whether the Voyagers could actually cross that boundary and go beyond it. Before we follow them there, it is worth pausing to appreciate what these spacecraft really are. By modern standards, their computers are primitive. A smartphone today is far more powerful. And yet the systems aboard Voyager were built in a way that made them remarkably adaptable. They could be reprogrammed and rewritten again and again, which is exactly what scientists have done over the decades. As the probes traveled farther from Earth, their needs changed. Some systems became unnecessary. Others became essential. In a way, the spacecraft had to keep reinventing themselves to survive. NASA gradually shut down non-essential components to conserve power and keep the missions alive as long as possible. Today, the cameras on both spacecraft are turned off. There is no longer enough power to run everything at once. Even so, the probes are expected to reach their 50th year in space in 2027 while still maintaining some level of contact with Earth. Their power systems are unusual as well. Instead of using fuel in the ordinary sense, they rely on radioactive material that slowly releases heat, which is then converted into electricity. The engineers who built Voyager promised extraordinary reliability. And considering that the spacecraft have operated for more than 4 decades in deep space, that promise was more than fulfilled. Most important of all are the scientific instruments aboard each probe. Each one was designed to measure a different aspect of the cosmos. And together, they gave us an entirely new view of the outer solar system. Voyager returned unforgettable images and discoveries. It captured volcanic eruptions on Io, one of Jupiter's moons. It revealed the delicate complexity of Saturn's rings. Not solid at all, but made of countless particles of ice. It recorded the most powerful winds then known in the solar system on Neptune, reaching about 1,370 miles per hour. And, of course, Voyager gave us the pale blue dot, the most distant photograph of Earth ever taken. That image was a gift from the edge of the heliosphere. But what exactly is the boundary the spacecraft had to cross? And why is leaving the solar system so difficult for any object at all? Before Voyager, nearly everything we thought we knew about the heliosphere was based on theory and assumption. Scientists imagined it as a roughly spherical bubble, but they had no direct measurements of its true shape. The speed of the solar wind near its limits, the role of magnetic fields, or even the exact nature of the material surrounding it. We did not know where it began in a meaningful physical sense. We did not know where it ended, and we certainly did not know whether anything human-made could pass beyond it. So let us define the terms clearly. The heliosphere is the vast region dominated by the solar wind and the sun's magnetic influence. The heliopause is the boundary where that solar wind is finally balanced by the pressure of interstellar space. Even now, its full shape and scale remain difficult to grasp. A useful way to imagine it is with something simple. Turn on a faucet and watch the stream hit the bottom of a sink. The water splashing outward across the surface is like interstellar space. The forceful, circular disturbance where the falling stream strikes is like the heliosphere. And the thin, unstable border where those two flows meet is like the heliopause. Scientists sometimes divide this boundary region into zones, including a bow shock, where the interstellar medium is disturbed, and a termination region, where the solar wind begins to slow dramatically as it collides with the surrounding environment. Thanks to Voyager, we know much more about this frontier than we once did, but still not enough. Voyager 1 and Voyager 2 crossed the heliopause at different locations and at different distances from Earth. That alone told scientists something important. The heliosphere is not perfectly symmetrical. Conditions vary depending on direction. And there was another complication. For a long time, Voyager 1 could not provide absolute proof that it had crossed the boundary at all. As our heliosphere moves through space, it travels within a larger interstellar cloud. Around us are other clouds as well. Right now, The solar system is still moving through its native interstellar cloud. But in about 3,000 years, it may begin entering a different region, sometimes called the G cloud. That transition lies far in the future. Of course, even at the solar system's speed through the galaxy, the distances involved remain enormous. Still, it raises an unsettling thought. In a few thousand years, the environment around the solar system may not be what it is today. And by then, the solar system itself may be far less hospitable. The actual crossing of the heliopause by the Voyager spacecraft became the subject of intense scientific debate. NASA officially announced that Voyager 1 had crossed into interstellar space on September 12, 2013. But that announcement came more than a year after the event itself. After months of analysis and verification, in reality, the spacecraft had crossed the heliosphere on August 25, 2012. On August 25, 2012, something extraordinary happened. Voyager 1 quietly crossed a boundary no human-made object had ever passed before. But how did scientists know it had happened? The instruments on board began to detect a subtle but unmistakable change. The extremely hot particles that normally stream outward from the sun suddenly dropped away. At the same time, another signal grew stronger. Cosmic radiation from distant stars and ancient stellar explosions began to increase. It was the signature of a new environment. The spacecraft had entered interstellar space. Not everyone was immediately convinced. There were reasons to question the data. The instrument that was supposed to measure plasma in detail had stopped working years earlier. Without it, some scientists felt that the evidence was incomplete. There was another puzzle as well. The magnetic field beyond the solar system was expected to point in a different direction. But it did not. To everyone's surprise, the magnetic field outside the heliosphere appeared almost perfectly aligned with the field inside it. Even today, scientists do not fully understand why. Then in 2012, a series of powerful solar storms swept through the solar system. Voyager 1 recorded the ripples of those storms as they traveled outward through space. When the waves finally reached the spacecraft, they behaved differently than expected. The signals echoed through a much denser environment than the one Voyager had previously measured. That was the final clue. Those echoes confirmed that the spacecraft had already left the sun's protective bubble. It was now outside the heliosphere. Voyager 2 crossed that same boundary later, in 2018, and its working plasma instrument confirmed the transition much more clearly. Yet the crossing of Voyager 1 raised even more questions. When the spacecraft first reached the boundary, its data behaved strangely. The measurements suggested that it had crossed the border not once, but several times in succession, as if it were drifting back and forth through a shifting frontier. Scientists believe the probe may have been moving through a complex region where solar and interstellar forces collide, a place where the boundary itself is unstable. Some of the data looks so chaotic that for a moment it was difficult to tell whether the spacecraft was moving at all. Its coordinate system seemed almost confused, as though the instruments themselves were struggling to interpret the environment. That confusion likely inspired many of the more mysterious stories that circulate online. But after careful analysis, scientists found no evidence of anything supernatural. The spacecraft itself continued to function normally. It obeyed commands from Earth and continued sending back signals. The most likely explanation is simply this. Voyager had entered a region of space that humanity had never measured before. When you send a machine somewhere completely unknown, strange readings are not the worst thing that can happen. They are often the beginning of understanding. Even now, the mystery of Voyager 1 continues. From time to time, the spacecraft has detected a faint, low-frequency hum. The signal is not a message, and it is not a voice from the stars. Most likely, it is the subtle vibration of interstellar plasma itself. As Voyager moves through space at incredible speed, The thin gas between the stars interacts with the spacecraft's instruments and produces tiny oscillations. Some scientists compare the effect to foam forming where ocean waves break along a shore, where the solar wind once pushed outward and interstellar space pushed back. The two flows mixed and created a turbulent boundary. Voyager is now moving through the remnants of that cosmic surf. The truth is that we still know very little about the region beyond the heliopause. Voyager 1 and Voyager 2 remain our only messengers there. They continue to measure the density of electrons in interstellar space by detecting radio waves created when solar eruptions ripple through the galaxy. As the Sun approaches the peak of its activity cycle around 2025, these signals may become more frequent. The data already shows something curious. The density of interstellar space just beyond the heliopause appears slightly higher than expected. Logically, scientists once assumed the density would gradually decrease. Instead, it seems to have increased. Small mysteries like this remind us how much there is still to learn. Voyager 2, whose plasma instrument is still working, continues to monitor the temperature of the interstellar medium. Astronomers expect it to be around 7,500 Kelvin. But the final answer is still uncertain. Every measurement brings us closer to understanding the environment between the stars. The ultimate goal of the Voyager mission has quietly changed over the decades. The probes are now attempting something no spacecraft has ever done before. They are sampling the untouched interstellar medium itself, a region of space so far from the Sun that our heliosphere has little influence there. The instruments continue to send their faint signals back across billions of miles. Each transmission takes more than 20 hours to reach Earth. And yet the connection remains. Two small machines built in the 1970s are still whispering to us from the darkness between the stars. Eventually their power will fade. One by one, their instruments will fall silent. But even then, the spacecraft will continue their silent journey around the galaxy for millions of years. Long after Earth has changed beyond recognition, Voyager will still be drifting through the interstellar night, carrying with it a golden record. A small message from a young civilization that once looked up at the sky and wondered what lay beyond. And tonight, as you look up at those same stars, somewhere out there, Voyager is still traveling quietly through the darkness, sending us the last faint clues about the vast ocean between the stars. So rest well beneath the sky of this small blue world. The universe is enormous, mysterious, and still largely unknown. But for now, our tiny planet is home. And somewhere far away, two silent explorers continue their journey on our behalf. Good night.